So today we're going to look at the final topic of our motion in electric fields section, and we're going to look at 2D motion in electric fields, and this links really well to our original topic of projectile motion. So just before we get started, I want to mention something. So we can link kinetic energy to the mass of an object and the speed of an object using this equation here. Ke equals half mv squared. Now, kinetic energy is measured in joules, and so is work. So we're going to link those two things later. I just wanted to show you this just to get it into your mind. So as I mentioned, this topic links really well to the motion topic we started looking at the beginning of the year. So when we described the mass moving in a gravitational field, we said, we linked the mass with gravity. Okay, so if our object we're looking at has some mass, we link it to gravity. If the object we're looking at has some charge, okay, now these objects will also have mass, but will have a charge, we link it to the electric field. Okay, they move in the same kind of way with a slight difference. So again, we're going to see our old friend Newton and one of his laws in play. So using Newton's second law to help us determine acceleration due to an electric field. Now we have these two equations, F equals ma, and we have our new electric field force equation, F equals QE. So if we say that those two F's are the same, then we can say the other parts are the same as well. So our ma equals our QE. If we divide both sides by m, these ones cancel, and we're left with an equation for acceleration. Acceleration equals charge multiplied by the electric field divided by the mass of the object. Okay, so we can work out the acceleration of a particle inside an electric field using this equation here. This is a really key equation. Okay, so let's have a look at an example now. So example 1, two large flat parallel plates, 2 centimeters apart, have a potential difference of 20 volts between them. A proton is fired upwards towards the positive plate. The initial speed of the proton is 10,000 meters per second. Calculate the force on the proton. So you can see here the protons down the bottom being as a positive charge being shot towards another positive charge. We know they're going to repel each other. It's not going to be attracted, so it's going to slow down. And we want to calculate the force on this proton. So we've got a couple of equations here. We know that the force equals the charge times by the electric field. Okay, we actually haven't been given the electric field here, but we can also work that out. So we know that's an and our electric field equals our potential difference divided by the distance between the plates. So I can put this straight into our equation, and I know that our F equals Q times delta V over D. Okay, and now I can just substitute in my numbers. Okay, so substitute those numbers into the equation, and we get our charge is 1.6 times 10 to the negative 19. Our potential difference is 20 volts, and our distance is 0.02 as given. So if we substitute these or put these into our calculator, we end up getting 1.6 by 10 to the negative 16 newtons. Okay, so that's the force, and that's going to be downwards. All right, so that's the first calculation. So the next part of the equation has asked us to calculate the acceleration on the proton. So we know that the force equals the mass times the acceleration. So we can rearrange this equation and say that the acceleration equals the force divided by the mass. Now we've calculated the force already, so we know our acceleration equals, the force is 1.6 by 10 to the negative 16, and our mass of a proton we can get off our equation sheet, which is 1.673 by 10 to the negative 27. Okay, and we can put that into our calculator, and that equals 9.56 by 10 to the power of 10 meters per second squared. and this is also downwards. Okay, because the force and acceleration are always in the same direction. All right, so calculated the force and now the acceleration. So finally, we've been asked to calculate the distance that a proton moves upwards in the space between the plates. Okay, so that indicates that the proton goes upwards, it stops, and then it comes back down. It doesn't make it to the other side. So what we know is we know the initial velocity, that is 10,000 meters per second. We know the final velocity. If it stops, it has to be 0. We know the acceleration is 9.56 by 10 to the 10. Now that's down towards the plate. So that's the opposite of our initial velocity. So we have to call that a negative. And using what we have, we can get this equation because we know all the variables and we want to know the distance. So what I can do is rearrange this to find the distance. And I can do that by just taking what I've got on the left-hand side and dividing by 2a. Okay, now I can just substitute into the equation. So our final velocity is 0 minus our initial, which is 10,000 squared. Divide that by 2 times by negative 9.56 by 10 to the 10. Okay, and if I put that into the calculator, so my distance, that equals 5.23 by 10 to the power of negative 4. Okay, that's a meter in meters, which is the same thing as 0.0000523 meters. Okay, and if we change that into centimeters, we get approximately 0.5 centimeters. Okay, so this thing comes up 0.5 centimeters. The acceleration causes it to stop at that point, and it comes back down towards the bottom plate. Okay, so we have finished that example. So basically the moral of this story was we can't forget these equations of motion. These have come up again, and they're not only important for the first topic, but they're also important in this electric fields topic. All right, so just again, we can use the kinematic equations, so the equations of motion, or the energy equations that we had a look at the start, depending on what information we are given. So you need to read the question, write down what you've got, and then work out from there. Now what we've done is we have determined that there's an acceleration between the plates, and it will be directly down towards the plate. So we need to describe motion moving perpendicular to the electric field and what shape it will look like. So we know that if we've got a positive charge like we do here, it's going to be attracted to the negative. And we've just discovered that there's going to be an acceleration directly up or down. In this case, it's going to be down. That's an A. Now, so once we enter this electric field, we can keep going straight. And as soon as we enter this electric field, we are going to be accelerated downwards. We're going to keep a constant horizontal motion. So what that means is constant horizontal motion and an acceleration downwards. It means we travel in a parabolic path. And that's why we can use our equations of motion. So there's a couple of assumptions we have to do in getting that parabolic motion. We have to assume that the field is completely uniform. We ignore gravity. Basically, we have to say it's a straight line path before it enters the electric field. As soon as a charge enters the electric field, it moves in a parabolic path, okay, because it has constant force in the same direction. And as soon as it leaves the field, it goes in a straight line because there's no force once it exits that field. Okay, I don't think those are too difficult to assume, but maybe they don't all play true in every real life situation, but for our equations and for what we're doing, these are going to play true. Okay, so what we have is vertical component of velocity. We call that Vy. Y as in y. If we have an xy plane, y is the vertical component. Now, if we're traveling horizontally, our vertical component is 0 meters per second. Okay, we know that. All right, so if we're moving this way, we have no velocity in the y direction. Now the horizontal component, that's constant. And why is that? That's because there's if we have two parallel plates, oh, that's a minus, okay, we have a positive coming in, there's going to be a force on it downwards. There's no force on it in the horizontal direction. So that means this has to be constant horizontally, and it's going to accelerate towards the negative and create a parabolic path, just like in our motion topic. Okay, so let's have a look at an example that links back to our energy equation. So what we know is the work done on an electron is 10 to the negative 14 joules, okay, which seems like a small amount. All right, but we're dealing with electrons, so we're not quite sure if this is large or big. And we've been asked to find the final velocity of the electron. So we know the work done equals 10 to the negative 14 joules. We also learned at the start of this video that the kinetic energy is half mv squared. Okay, so the work done is the energy given to the electron. All right, so if this energy is all given to the electron, it's going to turn into kinetic energy. So we can say that the work done equals the kinetic energy. And that means that our half mv squared equals 10 to the negative 14. Okay, now I'm going to times both of these sides by 2 and divide both by m. That gets rid of this half and gets rid of this m. Divide this by m. What I'm left with is v squared equals 2 times 10 to the negative 14 divided by m. All right, and to get rid of this square root here, this squared here, I take a square root. So what I need to put into my calculator is the v equals 2 by 10 to the negative 14 divided by the mass of the electron, which is 9.11 by 10 to the negative 31. All right, if I put this into my calculator, my velocity equals 1.45 by 10 to the 8 meters per second, okay, which is getting pretty close to the speed of light. Okay, so it didn't seem like very much work to do to an electron, but it's caused us to accelerate almost to the speed of light. Okay, so that's the end of the 2D motion topic for electric fields. Thank you.